And here we go. We have liftoff. Propulsion continues to be normal.
RCPA chamber pressure looks good.
Doubling up. Roger, with planet.
Water towers fly! Yes!
Tango down to nominal.
Flight Gammaray, SPD off. Bring in, SPD off. Off. It's orange!
45! Oh my god! Oh my god!
Decollage. Put that in the big bag, Tingle.
343 unfolds to go.
Indeed.
We rise together, back to the moon and beyond.
The methane will be igniting in the flare, correct?
Yikes. You dead? Sure. We don't need any more of these.
All right, folks, you know the drill. It's time for another Intrepid Museum Astro Live. John Galloway with NSF here. You know what's happening. Let me know if you can hear me and see me, because you're part of our remote production crew. Light budget here to get these shows done. But let's talk about the title of the show today. It's a really interesting thing. Spoilers behind me here, because it was right there in the thumbnail. I see that y'all are helping me out, and it looks like the audio and video is coming through correctly. But think of this, right? You always see these headlines on the news, and they're like, oh, we're going to go to an asteroid, and it's worth $18 quintillion or whatever, right? And everybody wants you to worry about how much an asteroid is worth. But nobody's over here putting in their headlines how much it's scientifically worth. Usually not. Like, you wouldn't click on that, would you? You should click on that if you ask me. But today here, we are not going to focus on what would happen if I suddenly had 1 billion tons of platinum show up in my backyard and how that would affect platinum pricing markets, market pricings, whatever. We are going to speak with some very talented folks from NASA working on the Psyche mission, so that we can learn what we're doing to get out there to Psyche. If you don't know, Psyche is a metal asteroid. We think it's a metal asteroid. I guess I should be a little bit more clear that we need to go and study it for a reason. But it may have been one of the, like an planetesimal, like a little core of a planet that's out there in the solar system, and maybe it didn't form, maybe it got crushed into by something or something along those lines. We're going to talk with folks today about what we're doing to go and learn more about it. And you think about it like, well, if we need to study the core of a planet or metal, why don't we just go down? We're on Earth right now. It has a core. It's metal. It spins. It makes magnet. Whatever, right? Why not just go down? Well, as it turns out, we've got other things in the way. We've got the crust and the mantle and all sorts of things that make it difficult for us to go down and study the core of our own planet. So if we could find the core of a planet just floating around out there in space with nothing in the way for us to study it, send beams at it, let the experts talk about exactly how they're studying it. But what we could do to study it, think of what we could learn about how the solar system itself may have formed if we're able to make it out to Psyche. So you don't come to these shows to listen to me talk. You come to the show to listen to the experts talk. Real quick, remember, we're able to do these shows with Intrepid Museum because of a grant awarded via the New York Space Grant Consortium. I can never say that quickly, but let's hop in and introduce our special guests and talk about why we need to launch a space probe to a metal asteroid. I should click this button. And we have more people on. Summer Ash, Lindy Elkins-Tanton, and Dan Waite. You know Summer before. You're going to learn more about Lindy Elkins-Tanton and Dan Waite here. Summer, take it away. Tell us about our guests and what we're going to learn today about going to Psyche.
I'm psyched for Psyche. I'm sorry I had to say it. But
it's out of the way. We don't have to say that again during the stream.
Yeah, right. One and done. And so today we're joined by the principal investigator, Lindy Elkins-Tanton, and an engineer and flight director of the Psyche mission. And so I would love to follow up on Das's intro and find out from you guys what the scientific value is of this mission and of the Psyche target.
I guess that's one for me on the science side. And I really like what Das said about the core. There are certain major ingredients that go into our habitable planets, like what makes the Earth so that it can have life. And one of the really critical ingredients is the metal core that makes our magnetic field. And there's the metal core for Mercury and Venus and Mars, and even the moon has a metal core. We are never, ever, ever going to see those metal cores. It's way too high pressure, way too high temperature. Even if we could develop the technology, the cost would be ridiculous. I mean, ridiculous. And so to learn about a metal core, we're going to go see a new kind of object that humans have never visited in our solar system, which is an asteroid that seems to be made mostly of metal and have a metal surface. And that's this asteroid Psyche. So we are going to outer space to visit inner space.
Ooh, I love that.
My husband said that. I totally credit him.
Hey, take it and run with it. I think that was great. So I have a question though, how do we know what we know about Psyche already? So like what tells us that is this possible metal world?
Oh my gosh, what can we tell from the Earth? And this is really important and something that's been really fun for all of us on the team. We don't have any pictures of Psyche. We're very spoiled humans. We're used to just like, I want to know what the moon Europa looks like. You just Google it and a million beautiful pictures come up. There are no photos of Psyche. We have shape models that people have put together from watching how things reflect off it as it rotates, and we have remote data. So the number one piece of evidence is its density. It's probably the densest known asteroid. Different estimates kind of edge it. It's like a neck and neck horse race with Cleopatra, this other asteroid. That's my hand holding our model. It's so that's approximately the shape of Psyche. Everything that you see on the surface is scientifically motivated, but interpreted by an artist, because we really don't know what it looks like. So the density says it has to be largely made of metal. The way light reflects off it says it has to be largely made of metal. The way radar interacts with it, the way its temperature changes. So these are things we can tell from Earth that tell us it's a different kind of world. And I don't know, Dan, is there stuff you want to add to this part?
Just the context of the whole science exploration in deep space, those beautiful pictures of Enceladus, and as the Juno mission's bringing back more pictures of, I think they had an Io flyby, it's awesome to watch the science data come out, and now we have these great images. But it's kind of a fun for the space geeks out there, just kind of walk back through and look versus time, how these images suddenly go from, we have this ground-based telescope to now we flew Cassini there, or now we flew Messenger there, and now we have all this great data. And so it's awesome that the Psyche mission is going to do that for 16 Psyche.
Yeah.
Totally agree.
I think I read that it's also estimated to be 1% of the mass of the whole asteroid belt.
Yeah, so it's not the biggest asteroid. It's got a dozen or more ahead of it in size. It's about, if you dropped it on New England, which is, not something we're going to do, but if you did, it's about the size of Massachusetts without the Cape. It's like the size of Switzerland, but its surface area is similar to California. So as asteroids go, that counts as a big one, but there are well over 1 million asteroids in the main asteroid belt, and Psyche is so dense that it does have about 1% of the density.
Psyche is the
mass of the mass. Sorry, 1% of the mass.
That's fair. And could there be other Psyches out there, or would we have already found them if they were that size? Like they could be something maybe smaller, but if it was the same size, would we know because of?
Yeah, if there were big ones in the inner solar system, we would have found them. And we don't super expect there to be big metallic objects in the outer solar system, but I'm just going to tell you we're probably wrong, because everything we think is wrong in the end when we discover new things. But there are about 9 asteroids that we're pretty confident are largely made of metal, but all the other ones are much smaller or they're bizarre shapes. And so to learn about a core, Psyche's our best bet.
Right. And so one of the big things, what's the big test for when we get there? How will we know if it is a core or not? Or what are the characteristics of a core besides the metal content?
All the amazing science instruments that Dan is figuring out how we're going to check them out and then make sure they work and send them. So this is a really interesting science question, because how do you design a suite of science instruments for an unknown object? How do you know you're going to be able to test your ideas? And so it really is all the instruments working together, and then a whole bunch of, brainy people really thinking about it and hashing it out. We're going to look for a magnetic field. Look, you're showing pictures.
Is this a science instrument? I'm pretty sure it's a science instrument.
That's DSOC. If you switch to, there should be one in there for the imager, and then mag, and then I think the Gammaray spectrometer. There's the magnetometer.
It looks like a disco ball.
That's the magnetometer. I'll just say a couple of brief words about it and then let Dan go on, because I think, Dan, your perspective from the engineering side is so important. We're going to look for a magnetic field. We're going to take pictures. We're going to get the topography. We're going to get the gravity field and the density. We're going to get the surface composition. And we're going to try to put that all together into a hypothesis. So Dan, tell us about what we're seeing up there.
So this is one of our two imagers. It's got the little telescope in there. It's got a charge couple device, so kind of very similar to any other digital camera. But then we have that kind of disc-shaped thing there. There's a set of filters in there. And then Lindy can talk more about this. But the idea is that we expect there to be certain elements in either, we want to determine how much of those elements are the constituents, at least on the surface of the body. And so we have certain narrowband filters that help us match the chemical signature of the things that we're looking for. We also have a wider passband that's basically the visible range for just what we would kind of think of like a black and white image. And we use that both for the overall topography, but also to navigate in our way in. And we can talk about the navigation in a bit too. But yeah. So as Lindy was talking to, there's this overlap of our magnetometer data, our GRS data, the neutral spectrometer, and then the imaging.
Did I get that right there? Did I circle the disc that you were talking about that had filters in it?
Yep.
And that thing sort of like can rotate, maybe not in that direction, but it can rotate to put different filters in between the sensor, which is on the back, and then this is the actual lens of the camera?
100%.
We talked about this in Skylab in the last show where they had to stick a screwdriver or something in to change the physical filters on the Skylab's telescope because it got stuck or something.
Do not even talk about that and stop showing blowing up rockets. You're totally freaking me out.
This one's fantastic. This is sorry, I was just looking at the way the filters rotate. Wanted to make sure I did the right side.
Yep. No screwdrivers though. They're just going to be perfect.
They are perfect.
I like it.
So speaking of rockets, how are we getting to Psyche? And it's coming up in October.
Yeah, go ahead, Dan.
So we're going to launch out of Florida on a Falcon Heavy. We're going to return the 2 side boosters, and then the core is going to be expended. And then the second stage, we'll go up and we go into a parking orbit for a little bit. We coast, and then we hit our injection on our way out. And what we're going to do is get on a trajectory that will eventually swing us by Mars. I did a fair amount of digging trying to see if we have our updated mission timeline and trajectory posted publicly, and I couldn't find it yet. I can talk to the old one, but so we'll launch out of Florida. Once we're in space, the vehicle itself will do its own. Brought my props. Our conference room. So we have our little Psyche model with our little directional antenna and our little solar panels.
Yeah, but they're not little, they're huge. Yeah.
They are my little like toy version of it. But yes, they are huge. So, for scale, a human's about, half the size of the vehicle. So, but the solar arrays will fold up alongside. Yeah, there's the picture. And so you can see the folks in the clean room there working on it and how much smaller they are. And so we have one set of array on one side and the other set of the array on the other side. And in this particular picture, there's only 3 of the 5 panels on that wing. The other 2 wrap around that center panel there. And so they all fold up so we can fit in the fairing on the Falcon Heavy. And so that will be what the vehicle has to do is once the Falcon, the SpaceX folks let go of us, we deploy the vehicle deploys its solar arrays, points itself to the sun, and then it basically phones home and says, okay, I'm here. Now help me out, figure out what we need to do. And then we check out all of our science instruments. We check out a bunch of the different things on board the vehicle. And that takes us a little bit of time. We do all that checkout, and then we start thrusting on our way out there.
How long will it take once? So how long will it take to get to Mars? And then are you doing a gravity assist around Mars?
We are doing a gravity assist around Mars. I want to say we're about 1.5 years. I'm trying to remember that data.
May 2026, I think, is Mars gravity assist.
Okay.
Yeah.
Now, before we started, Lindy, you were talking about the dates of the launch window, but there was something even more wild about the launch window because we're used to hearing hours. And you were saying it's like seconds or less?
Yeah, I will just share with you my astonishment when I learned this as principal investigator, and then Dan can explain why this is. So just to let everybody know, we have a launch period, which is the number of days, and NASA requires, I believe, at least 20. Is that right? Or is it just over? Yep. Possible launch days, October 5th through 25th of this year. And so we expect to launch at 10:38 a.m. Eastern time on October 5th. and we'll launch on that Falcon Heavy, and they will reland the side boosters with the most mind-crushing sonic boom, and it's completely exciting. And then about 60 minutes later, we will separate from the rocket and begin all those other things Dan was talking about. But the thing that blew my mind is that's the launch period. Every day there's what's called a launch window, is the amount of time that you could launch during, and you would still be facing the right way and everything would work for your trajectory. We don't have launch windows, we have launch seconds. We have an instantaneous launch second during every day. So Dan, can you explain that? Because that was shocking to me.
Yeah, and so especially for our deep space missions, it's really not that unusual because, you know, if you're going to an Earth orbit, Earth's here, and so there's an orbit you want to achieve, and so as long as that orbit kind of passes overhead where you're launching from, and you can do some steering with the vehicle, you can get into that orbit. But what we're trying to do is we're leaving Earth orbit. So when the Falcon drops us off, we're no longer in Earth's, Earth is no longer the central body of the vehicle. And so the vehicle is going to be on its way out. The sun will become the central body. And so what we want to do is we want this very special trajectory that our navigation team has worked so hard on to get to the point where, and we should talk, because the science architecture of how we orbit Psyche, 16 Psyche, is astounding, right? And so the navigation team said, I have to get here at this time to get the lighting, to get the science. And then they backed all the way out. And so we have to hit that corridor. And so when we get launched, we have to take into account all the things that the SpaceX folks need to deal with the Heavy to get clear of all the population centers, all this other stuff, make sure that we're good to go there. And then we go into kind of a parking orbit for a brief period of time before our parking orbit intersects our trajectory on our way out. And so that's why we have this kind of instantaneous launch window, is we have to do all this math and we don't want to mess up the math. And so we work it out, and it's basically, I'm going to get to my parking orbit at exactly the right time, and then I'm going to inject into my Mars-bound trajectory.
Yeah,
so that windows that down.
Real quick, I'm going to put this link into chat. There's a really fantastic site, psyche.asu.edu, that has a ton of resources on it, and the graphic that I'm showing you is straight from the website right now. So if you all want to explore that a little bit, you were talking about the trajectory and how we're going to get there and the Mars Assist. I'm going to put this in chat so people can click on it and sort of explore a little bit more in depth themselves.
It's a good website.
It really is.
It's a great website. It's awesome. And that's the great thing about being able to do a webcast like this and all this information in here. But as I was kind of poking at a little bit earlier, the overall shape of our trajectory is about the same. But because we want to get the vehicle to 16 Psyche at this time to get the lighting that we need to achieve our science objectives. And Lindy, you should talk about why it's really hard to get the lighting. This is the 2022 mission trajectory. For 2023, we actually do basically another half lap around the solar system. And so what we'll do this time is, rather than going as it's shown here, we kind of go and do the Mars gravity assist right away. The 2023 trajectory, we launch out past Mars. We don't even do the MGA on the way out, and we do it on the way back. So our original orbit is going to be this kind of elliptical thing that goes part way out towards Psyche, and then we zip back around past Mars and do the gravity assist, and we get about another half lap of the solar system. Which is all to get.
Tell me if I got this right. I mean, clearly I'm not an astrodynamicist, whatever, but it's more like that, where it goes a little more elliptical than zips past Mars?
It's a little bit more elliptical, and I think Eyes on the Solar System has this trajectory that you can kind of watch the animation. The interesting thing is this is just a fixed image of everything. Everything's moving in the solar system. That's part of why the nav problem is so interesting, is that we have to actually fly by Mars, but Mars isn't just sitting still like it's kind of shown in the cartoon here. And so we have to be able to thrust and then coast and then catch Mars on its just the right time to get the gravity assist, so we can get back out to 16 Psyche's orbit. Need to be careful with that. 16 Psyche, when 16 Psyche's there, it doesn't count if we get the spacecraft, which we call Psyche, out to 16 Psyche's orbit, but Psyche's somewhere else in its orbit at the time.
We can always fall back on Asteroid and spacecraft. And I think one thing that Dan's referring to that maybe not everybody knows is that we had been originally selected to launch last August. And so when we're talking about a different trajectory, it's because we weren't ready last August. And so we went through a very exciting independent review board process and reconfirmation.
Welcome
through
to Eyes on
NASA
the Solar
to
System,
launch this
where
year.
you can
And
explore
it
your
turns out,
planet.
because all the objects around the sun are in different positions now than they were last year, we have a longer, more complicated trajectory that takes us around the sun one more time before we go out there.
Yeah. So, Dan, you started mentioning that it sounded like that the orbit, once we get there, is interesting for the science that we need to do. So I would love for you to talk about that, but then I definitely still want to hear from Lindy about how we figured out like the lighting and that moment of arrival and why that's so important.
So in terms of the orbit architecture, each of our science instruments has a kind of a happy place where it wants to be to acquire the data that we want to support the science investigation. Turns out that, like a family, like a team, they're all slightly different. And so we want to be at different orbit radii to acquire the data that we want for our imaging and topography and for the gamma ray and the neutron spectrometer, and then for our gravity science. And so the awesome thing about our electric propulsion system is that it allows us to arrive at one orbit, collect the data for that one investigation campaign, and then we can morph that orbit. And so I'm really excited about what we're doing in the 2023 mission design, because the navigation team came up with this way of, we have this electric propulsion, we have this lighting situation. And so what we do is we step the orbit down in radius, but then we rotate it 90 degrees and shrink it quite a bit. And so the navigation team on the Dawn mission did something very similar, where to get a different science, they actually moved the vehicle further out away from the asteroid and then brought it back in. And that's the cool thing for orbit people. These solar electric propulsion missions are awesome. If you're excited about orbits, go find a deep space solar electric propulsion mission to study.
Yeah, it's amazing, just amazing. The other thing about the orbits needing to step in is that Psyche is not a sphere, and we don't think it's homogeneous in its density. So it's going to have a weird gravity field. And so we do need to start pretty far out and determine the gravity field and then calculate the next orbit closer that's going to be stable. And imagine it's shaped like, I always say it's like a potato, because potatoes come in many shapes, and I'm not wrong. Therefore, no matter what it is, it's shaped like a potato. And but imagine you had a potato where one end is all metal and the other end is all rock, and the metal end is twice as dense as the rock end. So the metal end could have very high gravity, and the rock end could have much lower gravity. It's going to be a challenge. So we did a Monte Carlo suite of 1,000 practices to make sure, simulations of how crazy could the gravity field be, and prove that we could still find stable orbits very close in. So that was a great part of it. And then briefly about the lighting thing. So I think probably most everybody who listens to this knows what the ecliptic plane is. It's the plane of the orbits of the planets around the sun. And so we're used to looking at the planets when we look at images of them as if we were standing on that ecliptic plane, and we see the Earth with its spin axis and it's spinning like a top, kind of up and down. Psyche has been hit by things, presumably, and its spin axis lies almost exactly in the ecliptic. So instead of spinning like a top, it's spinning like a rotisserie chicken. And so if I'm going to make the sun with one hand, and then here's Psyche's spin axis, you can imagine there's times of the year when only the North Pole faces the sun. Wait, how am I doing? There we go. Only the North Pole faces the sun. And then as Psyche goes around, then it's side on, and then as it's rotating, it's lit all over. And then as it goes on, there's a time when only the South Pole is facing the sun. So if you want to get pictures of the whole body, you can't run your whole mission during the time when only one pole is being lit. You've got to get parts of the mission when it's sideways to the sun, like a rotisserie chicken, being lit all over as it spins. It spins about once every 4 hours. And so its orbital time around the sun, its year, the Psyche year is 5 Earth years. And so getting that timing right is really something. And so Dan did mention that the trajectory artists, who are just amazing, they pick when we need to arrive to get the lighting we need, and then they try to back calculate a path that brings us to Cape Canaveral, basically. Yeah.
I love that phrase, trajectory artist. I want to be that.
Lindy, I'm going to attempt to draw what you just said.
Go
because
for it.
I sort of get it, but here you can see the sun would be sort of in this area. That's my sun drawing, right? And it's
Love
sending
it.
photons this way and lighting up that side. And the Earth sort of has an axis like this, and it spins like that, right? So the sun rises in the east and it sets in the west, and it's because the sun the Earth is spinning, right? And Psyche's spin axis is not up and down relative to the sun like that, but again, this is rough. I'm not a planetary scientist.
Roughly.
Yeah, its spin axis is sort of like this. And when it spins like this. And
that's
so
the rotisserie chicken.
Yeah, I could try to draw a chicken. I could maybe like draw a drumstick on there or something, like a Psyche drumstick.
Excellent. That's not going to confuse anyone. That's
definitely
great.
It's like, what happened to Psyche? Plus metal, it would not be great for a chicken. But when the sun, like as it orbits the sun, right, the sun is always going to be illuminating this side over here, and this side's always going to be in darkness. Well, sorry, I said that wrong. At any given time, this side is going to be illuminated, and this side's not going to get any illumination. And then as it orbits...
For about a quarter of the year, right?
A quarter of the Psyche year?
Yeah, the Psyche year.
The Psyche year, okay. And as it goes like its way around the sun itself, Psyche's orientation stays, and the sun sort of moves relative to Psyche. So the sun's going to end up over here at some point. Am I getting that right?
Yeah, I think you might have your direction around the sun not right, but that's
I'm looking from the bottom.
You're looking from the bottom. So that's
Sorry.
the beauty, right? That's the beauty. So we're standing on the ecliptic plane, but the other way around. We're Australian today.
Sure.
We're Australian.
I'll send it this way. I can send it that way.
You're exactly right. You're exactly right. So then when the sun's on the side, you can picture how it would get lit completely as it rotates around.
As it rotates. Gotcha.
Yep.
And then the sun ends up over on this side, and you have this part that's going to get a lot of sun, and then this part that's going to get no sun, as I just...
Absolutely perfect. And then imagine for a second what that means in terms of heating. You have all your solar heating on one end, and it's freezing cold on the other. And so it's very, very interesting scientifically. What would happen if you had an impact crater on that freezing cold, dark pole? Because the material properties of the surface will be different at those temperatures. And Dave Stevenson, a fantastic geophysicist at Caltech, was talking to me once about this. And he said, it's possible that the cold end of Psyche is so cold that metal at those temperatures would shatter like glass if it was hit by an incoming meteoroid. So this is just a sample of the crazy places our minds are going to this unknown body, because we're going to see things we've never seen before.
Can we talk about this splash, like metal splash mark on the rim of the crater here? Like, is that...
Yes, we can talk about that. All right.
What are these? Splash mark first. There's so much stuff in this rendering. Tell me what y'all were thinking.
So many things. You're thinking, so this rendering is done by the fabulous Hollywood artist, Peter Rubin. He's worked on Ghostbusters. He created one of the S's for Superman that's copyrighted. Like, he's done all these amazing things. And he and I Zoomed on weekends for like a year while I tried to explain to him all the science ideas we had about what Psyche could be. And he tried to create them into art. He totally succeeded. And so one interesting question we have is, if there are big regions of Psyche's surface that are made of metal, what does a crater in a metal look like? First of all, it's only recently that humans could even wrap our mind around the idea that these are hypervelocity impacts and they're not volcanoes. That's what craters are. They're hypervelocity impacts. The physics of them are pretty much outside of our everyday experience. And so we've seen craters on rocky bodies like the moon. You can see every time you see the moon, you see these beautiful big craters filled with basalt. That's the black lava that's frozen in them. You can see craters on Venus and on Mars and all the different places. And then we've seen craters into ice. And we kind of have modeled how the physics of ice cratering is different than rock. We've never seen craters into a metal object because we've never seen a metal object. But what we have done is we've done hypervelocity gun experiments, like in the Ames vertical gun range, where they shoot projectiles into targets. And in fact, we've even done that on our team. Simone Marchi at Southwest Research Institute got blocks of metal meteorite. And I'm going to hold this up to my screen and show you a picture of a metal meteorite. And so here's a beautiful, it's an iron nickel meteorite. This is more or less what we think Psyche's made of, and it has that plaid pattern of nickel iron crystals called the Widmanstätten pattern. So he took blocks of iron meteorite, cooled it to space temperatures, and then shot hypervelocity projectiles into it to see what the craters look like. And in fact, in little craters like that, the liquefied metal freezes before it falls down. In rocky craters, the ejecta just falls down. But in these metal craters, little rims stick up because they froze before they fell. We don't expect this to happen on craters as big as the one that we're imaging in this picture or imagining in this picture. But smaller craters on Psyche probably will look like that. They will look so weird. And so that is part of our fun hypothesizing there.
I am so glad that you brought up the Ames thing, because I am obsessed with the fact that at NASA Ames, they have that high velocity gun. And it's, I think, up to 16,000 miles per hour or something. Yeah.
It's another mind-blowing piece of tech, right?
Yeah, I once visited Brown because I was curious about potentially going into planetary science. And I feel like if I had done it, I would have wanted to do cratering, because the faculty was telling me about this gun. And so they can really shoot things at all different angles and all different materials into other materials to try and replicate what you think the thing is. And yeah, I think, is DOS zooming, are you zooming in? Because are those like also ejecta that would freeze like
frozen droplets? Those question mark is good. That's a good label for that. Yeah, like frozen droplets of metal ejecta. Yeah.
I wasn't gonna get past that without circling those things. But again, this is,
looked at that so closely.
This is all the sort of ideas, like hypotheses, things that may be true. And the reason we need to go there and inspect it more closely is so we can see what's true and what's, I guess, not true. Like what is supported by the evidence we can collect, and then what was, well, it doesn't actually work that way, but it was cool to look at, you know?
This is a very important thing for everybody who's listening to realize. What Dan tells you is factual truth because he's built it with his hands. And what I tell you is science hypothesis based on some good knowledge that we have, but we do not know about Psyche yet. So probably all the hypotheses I tell you about Psyche today are not true. We're going to be proven wrong when we get there. And that's part of the thrill of exploration.
I labeled Psyche here exists. And I guess
thank you. That's a very good key right there. And then you could write imaginary.
Yeah, imaginary, right? Cool idea or something. Imaginary is such a long word to write and spell correctly live on the stream.
Give up. It's really important. Good job.
Yeah, there we go. Okay, cool. But that's part of what we do. Like we haven't been there. We don't know. And so we have all these great ideas that may or may not be true, supported by our understanding of physics and the universe and things and all this sort of stuff, right? And that's why it's important for us to go there and figure out what's true and what doesn't work that way.
Yeah, I wanted to ask about two related things, because Dan, you were mentioning the calculation of the orbits, or how it sounded like you were saying we won't know till we get there how that we can calculate or figure out those stable orbits, like you did the Monte Carlo analysis, hypothetical, knowing that you could find one, but we won't know until we actually get there what the distribution of mass is in the planetesimal.
Right. And that's why we do the Monte Carlo, is we have, so the fun thing with the Monte Carlo is that idea of effectively kind of there's these set of random variables and there's multiple that we can play with all at the same time. And so we have a group of people who, you know, Lindy and the science team talk about what they think the gravity field might look like, what the mass distribution might look like. And then we actually, you know, plot, okay, well, we're going to have a distribution for this characteristic, a distribution for that characteristic. And then we run the analysis where we sample all the parameters that might matter, and we produce the run, and then we adjust the orbit, like we see how the orbit plays out. And then we try to control around that. We say, well, we have a thruster with this much thrust. We have a way of determining what our orbit actually is and how we can propagate that forward. And so we wrap a control system around that, and we say, okay, given this potential distribution of mass at the asteroid, how can we control around it? And that's what our navigation artists do, is they take all that into account, and then they say, okay, yeah, with that thruster, with this much power, with this kind of radio system, we can determine our orbit and we can control around it.
And I read something that was talking about using radio communications to do the gravity mapping. Can someone explain that in a little more detail? And then can I also confess that I have to get my power cord because I forgot to plug in my computer. So I'm out of frame and I'll be right back, but please go.
Go, Dan.
So I can talk to the technical part. The part about how we actually convert that into science data is, I'll hopefully Lindy can backstop me on that one. So the great thing about deep space navigation is we don't have a global positioning system in space. So the spacecraft itself, we have to tell it where it is. but it can't figure out where it is, and so we have to help it figure that out. We have to do all the math on the ground, and then we have to send information to it to say, okay, here's where you are relative to the asteroid, relative to Earth, relative to the sun. And the way that we do that is for the majority of the mission, we use this radio signal. So we communicate with the spacecraft, we send a signal up to the spacecraft, and we get a signal back. And so that radio link is great for us because we can do a couple tricks with it. We can actually do, I'll talk through three. We can send a signal from the ground up to the spacecraft, and the spacecraft, when it sees that particular signal, routes it right back with a known delay. And so we do a bunch of math. We figure out how long the atmosphere delays that signal. We have relativistic effects, all these other things. And we say, okay, given the speed of light and how long it took for that signal from the deep space network up to the spacecraft and back, here's how far the spacecraft is from Earth right now. And it's even more fun than that because here's where it is from the center of the RF of the deep space network right now. And so we integrate that and we have, okay, now we have a radio line. Then we can look at the frequency shift, and we can actually figure out how quickly the vehicle is moving away from us, usually away, sometimes towards, by the Doppler shift on the signals. We have our deep space network, which is this an incalculable asset to all of this space science, all the things we do with the deep space network. And so the frequency stability of the deep space network is great. So we can pick out this Doppler shift of the vehicle moving at fractions of a millimeter per second. Right, so we can calculate the velocity of it with the Doppler shift, and then the last one we do is, because we have deep space network complexes on different sides of the world, we can actually send a signal from one deep space network complex up to the spacecraft and back down, and we'll use that baseline. So for our radio astronomy people, we're familiar with the long baseline interferometry. We can do something kind of similar with the deep space network because of its positions. And so now we've got a radial measurement, we have a velocity measurement, and we kind of have a spot in the sky. We integrate all that, and now we can figure out where the vehicle is. And so we do that at the orbit, and now we can kind of see how the vehicle is moving, not just with respect to Earth, but with respect to Psyche. And because we have that great Doppler measurement, we can actually see as it's moving, as Psyche's mass is kind of moving that orbit around, we kind of get these little bobbles in the Doppler signal. We integrate that, and now we have gravity science. Awesome.
I'm such a nerd. I love all of that you just said. And I love the deep space network. So if anyone's watching and they don't know about it, I think you can go through the eyes on NASA, but the DSN Now will show you those 3 antennas in Goldstone, California, Madrid, Spain, and Canberra, Australia, and tell you which satellite, which space probes it's talking to.
There you go.
Once they're talking to it, you can tell it more about the antenna, or you can ask for more about the spacecraft. It's so cool to just be like, oh, here's who we're talking to now.
And Dan, what's our 3-letter call sign for the Deep Space Network so people can watch for Psyche comms when the time comes? Oh, I asked you a great question. I'm not sure it's PSY, actually. I think it might not be.
Yeah, I actually don't know. I haven't... I will check that out. Sorry.
Yeah. No, I don't remember either. Sorry, I didn't mean to catch you out.
No,
I just
it's okay.
assumed you would know, and I forgot. So anyway, when the time comes, people can be watching. And I don't have much to add to what you said about the radio science, because that's exactly right. But maybe the one thing to add is, if Psyche was a completely homogeneous material, then the orbital speed, if it was in a circular orbit, the orbital speed would be constant. But because Psyche is not homogeneous, presumably, just like the Grail spacecraft did this for the moon and Grace did this for the Earth, you can actually figure out the densities, because if the spacecraft's coming over a high density part of the surface of Psyche, it'll be pulled forward a little faster and you'll get one of those bobbles in the Doppler. And then when it passes it, it'll be slowed down a little bit by the pull backwards by that extra gravity. And so amazingly, you can integrate through all of those bobbles that Dan mentioned and actually figure out what the density of the surface of Psyche is.
That's so
and therefore the gravity field. Yeah.
Hey, are you getting a pile of questions at all yet? I just thought I would ask.
You saw what monitor I was looking at, probably off on the side. I have a ton of questions, and when you said you were a total nerd for this sort of stuff, it looks like there are a ton of people in chat that are total nerds as well, because I have never seen I'd never seen so many fantastic questions on a
Oh my
single
gosh,
stream.
yay.
No.
Okay.
So there's no way we can get through all of them. Y'all, you know how we do these streams. Like, we want to take some of your questions live. I'm not going to be able to get to all of them. I'm going to try to combine some of them and that sort of stuff. But let me get a couple here. And some have already been talked about. Like, one is asking what the launch window is. We've already talked about the launch window a little bit and how it's some number of days, but it's an instantaneous 1 second window each day because of orbits. How do they work, right? But let's grab this. This is...
Yes, you're totally following. Perfect.
This is, here is a question from Paul Kelly, and it says, is Psyche totally unique in the solar system, or is there something similar but smaller, something similar but bigger? Do we expect to find Psyche farther out in the solar system, or something similar to Psyche 16, 16 Psyche out of the solar system? Like, talk to us about how unique it may be and why that makes it a good target, I guess. Lindy?
Yeah, so Psyche is a unique object, and humans have never visited something that seems to have a metal surface, like I was saying. So it's primary exploration. There's this table you're supposed to fill out in your step 1 proposal for NASA, which is what percentage improvement is your data over the existing data? And we just had infinity, infinity, infinity. So there are about, as I mentioned this briefly, there are about 9 asteroids in the main belt that people think probably have some metal, extra metal in them and are like Psyche, but none of them are as big as Psyche. The one that's closest is this fabulous asteroid Cleopatra with a K, and look it up because we have photos of that one, and it's shaped like a really elongated dog bone, which to a fluid dynamicist says it was a liquid that was spinning, and that would make those bulbs at the end. And so it's some sort of impact fragment, probably. Not going to tell you the same things about a core as Psyche, which is, if it is what we think and hope it is, a big chunk of some metallic core. So Das is going to find a picture of Cleopatra.
I was trying, but it's a very difficult. There's Cleopatra from Wikipedia.
Not a great picture, but it's a picture.
It's a picture. It counts.
Better than what we have for Psyche. So there are probably other things a bit like Psyche. Whether we expect them to be farther out in the solar system, generally no, because the sort of the canonical view of the solar system is that the heavy rock forming elements are concentrated in the inner solar system and the ices and gases are in the outer solar system. But that's also not true, because one beautiful example of how that's not true is that cometary ices are known to contain little olivine crystals, olivine being like the poster child of the rocky planet's rockiness. And so what the heck are they doing out there in comet ices? So there's a lot of mixing. And so I would say, from my kind of skeptical point of view, that we're going to find surprises in the outer solar system that we are not expecting. And it would not completely shock me to know that we find stuff made of metal that got flung out there too.
Gotcha. There's so many questions here. Like, I'm just going to speed run so many questions instead of me now talking about the same question for another 5 minutes, right? How about this? Is Psyche likely to have heavy elements like uranium? Would they be mixed in with the rest of the metals, or would we not expect to find them out there?
There'll be some uranium, and so I can't remember the name of the brilliant geochemist. I guess it was Goldschmidt, actually, who figured this out, that you can take the periodic table of elements and you can define every element according to what phase of material it likes to live in. And so there are atmophiles that like to go into the atmosphere, and then there are lithophiles that like to live in rock, and then there are siderophiles that like to be dissolved into metals. And so the metal part of Psyche will have all of the siderophile elements. We expect the metal part of Psyche, here's another prop, to be like a metal meteorite like this one. And you can see the metal part is the outside. Wait, it's not quite in focus. Come on, camera, you can do it. How are we doing? It's okay.
It's good. Yeah, it's good.
Yeah, the gray part on the outside is the iron nickel metal. And then that blob in the middle is troilite. It's sulfur and iron pretty much in equal quantities. FeS is troilite. So we expect that to be also part of the metal material. It becomes an immiscible liquid. As the core freezes, the core divides into 2 liquids like oil and water. The oil one is this sulfur-rich troilite, and you could see it was once a liquid blob, and then the metal part. So stuff that likes sulfur goes into the sulfur troilite, stuff that likes metal goes into the metal phase. So you get iron, nickel, copper, and then you get all the other good stuff. Iridium, rhenium, platinum, palladium, gold, silver, you name it, in tiny percentages. Uranium, weirdly, we think of it like it's a metal, but it's not. It really would prefer to be in a fluid phase, and so it's water activated by water and dissolvable into water. So probably there is uranium in tiny particles, like someplace in the surface material of Psyche, but hard to know.
Gotcha. We have the right people on the stream to answer all of these.
Yeah, hopefully that wasn't too long an answer.
No,
I
no,
got backed up too far.
No, it's fantastic. People are. It's almost like they're trying to stump us, but we have the experts on.
Right.
I wanted to say it's a really good thing that you're not defining metals by astronomy standards, because every hydrogen and helium we call a metal.
That freaks me out, right? Everything in the solar system is made of X, Y, and Z, where X and Y are hydrogen and helium, and Z is everything else.
Everything else. I want to ask this one. This is one from James Atkinson watching, and I've seen a YouTube video where they do this, right? Where it's like, I have a strong magnet, and then I heated up my strong magnet, and now it's not a very strong magnet, right? And then they do something and they remagnetize it. But we know about, or we hypothesize the metal core of the Earth, and the motion thereof helps us create our magnetic fields, which helps shield us from radiation and stuff like that. And if Psyche is getting hit by these hypervelocity impacts that are superheating metals, what might that say about the magnetic properties that we may find on or around Psyche?
Should I take a stab at this, Dan? Yeah.
Go for it.
Yeah, so magnetism, a hugely complicated and mysterious subject.
How do they work? Magnets.
Right. So we think that, right, I'm going to tell you all this stuff. We're going to start with quantum, okay? But okay, we'll start with algebra. We'll work up to quantum.
Nice.
So in our Earth, we have a liquid outer core and a solid inner core that are made of metal. And the outer core is convecting because it's losing heat from its top, and that causes material to advect up and down. And the metal acts basically as an electrical current. And every electrical current makes a magnetic field around it. So in a super simplistic way, that's why we've got a dynamo on our Earth. Now, you make a rock on the surface of the Earth, say out of liquid magma that erupts out of a volcano. As it cools, it's in that Earth magnetic field, and its crystals, actually the atoms in its crystal, align to the magnetic field, and it freezes a record of that magnetic field. It itself is not creating a new magnetic field. It's just a static magnet of its own. That's actually called remanent magnetization, not remnant. If you're a cool kid, you call it remanent magnetization. So that's what we're hoping to find on Psyche. Psyche will not have an active dynamo. If it was a core, and it is a part of a core, and if, back in the day, 4,568 million years ago, when Psyche was a baby and it had a liquid metal core, it probably had an active dynamo like the Earth's. Then, if it froze from the outside inward, those outside layers of metal can freeze the magnetic field and hold on to its remanent magnetization while the inside cools. Any rock on the inside would be too hot to freeze in that magnetic field before the dynamo went away. So you need a rock that's cooling through a temperature called its Curie point, where it can freeze in that magnetic field while the dynamo still exists. This seems like this is special pleading, like this could never happen. I had so many ifs. But practically every iron meteorite that we have here on Earth has remanent magnetization. So it happened over and over and over and over again, because these are all little bits of metal cores. So that's what we hope for from Psyche. And then if it had hypervelocity impacts on its surface, the magnetic field would be altered from the heat of that impact, but it's local.
It's local. Gotcha.
So that's like a nutshell of a very complicated suite of things. Yeah.
It's really cool. I've never thought about that, where you heat up a metal and then it sort of makes a record of the magnetic field. It makes sense once you think about it. Like the crystals align a certain way along those force lines from the field, but I've never thought about that.
That's how geologists figured out what mid-ocean ridges are in our oceans, because parallel to the mid-ocean ridge, you have swaths of crust that froze during different epochs of the Earth's magnetic field with positive and negative remanent magnetization in them, frozen in.
Well, I've learned something. We can stop the stream. We've accomplished
cool.
It was a good deal.
Done.
Thanks everybody for watching. No, there's probably people in chat who are still learning things, so we should probably keep going. Do
you have a good engineering side one for Dan?
Yes, actually, that's the next one here. I would probably have to find it again real quick. But there were some questions about how we'll be studying the materials or the composition of the asteroid of Psyche, of 16 Psyche is the right way to say it, right? With the instruments we have on the spacecraft. And we talked a little bit about it, and then I'm starting to bring up images of it, but we didn't really get through a bunch of the different instruments. So Dan, can you talk about some of the instruments that are going to be inspecting and gathering data and stuff like that for us, specifically to learn about Psyche, and I'll bring up the images that are labeled that way.
Okay. So we have, and we tend to, so we talk to the magnetic field. So if you bring up the magnetometer image again, we've got that. And talk a little bit about how the engineers worked with the instrument team to kind of figure this out. You'll notice that these are on this boom. And the idea is that what we want to do is we want to sample this remnant magnetic field. If I need to join the cool kids club, and so I want to try to use
Thank you. That was excellent.
And so we attached the two magnetometers to this boom, and so we can actually kind of measure, because we have the two separate measurements, we can get a little bit more of the dynamic of the field here. And then on the opposing boom, we have the gamma ray and neutron spectrometers. So these will measure gamma rays and neutrons coming off the surface of the body. And so we know where the body is with respect to the sun, and we can kind of get that image as well as the magnetic field. And then the imager would provide, especially with, so we'll convolve two different things. We talked about how we would build a gravity model with the radio science measurement, but the other thing we do, so this is the gamma ray spectrometer, the neutron spectrometer is right behind it, but it's on the other, so this is the opposing boom on the other end of the spacecraft.
I guessed, Dan, because it was GRS, and I was like, gamma ray something. Yes. I bet you that's the gamma ray one. I was guessing with the problem.
Acronym master.
Sorry, I was trying to show it when you were talking about gamma rays, but
it's okay.
Keep going.
And so we've working with the science team, and then the instrument team did all the great engineering to develop these particular instruments for this particular campaign. So the gamma ray spectrometer in particular, we're looking for gamma rays of a particular energy. And so we had to actually work with the instrument team to come up with, okay, we want to look for these particular gamma rays to help check this box on the science. And so these are the two booms. Actually, if you go back to that one.
Thank you,
So that's Lindy, and then Brian Bone, right? Was that you and Brian there?
It's me and Brian, but the instruments aren't on yet. I know you have a picture of the spacecraft in Florida from last week. It's all covered with blanketing, but you can see the booms and all the instruments. I think Des will be able to find that in a second.
Yeah. And so we move those instruments away from the vehicle so that they don't sample the vehicle. That's the other kind of fun thing. So in an ideal world, we would just have these perfect instruments in their perfect position, and there would be nothing else there. But we need to provide them power. We need to keep them at the right temperature. We need to extract the data from them and relay that data back to Earth so we can send it to the science team. The science team can do all this wonderful science with that data. So the magnetometers are on, in this image on the left-hand side boom, the gamma ray spectrometer is on the upper end of the right-hand side, if I've got my sign convention right, and then the neutral spectrometer is halfway down on that boom. And so these allow us to kind of sample the magnetic field and then things coming off of the body. The imager allows us to collect the visible wavelength photons coming off the body. And then the other neat thing we do with our gravity science measurement and then the imager is that we can build a three-dimensional topographic model. So we can actually, like that artist rendering, which is awesome, of all the different shapes, craters and boulders and things like that. We can overlay all these images and then start building this three-dimensional model from the images that we have. And then we convolve all of that together to say, okay, there's this kind of feature over here that has a lot of mass that is indicating that it's got this kind of composition based on, and they've got a magnetic field around here. So you can do all that math and then start puzzling out, what are you looking at? So that's the fun for us on the engineering side, is saying, how do we design the instruments to answer these science questions, and then overlay all of that, and then provide that for the science team.
Gotcha. I think I found the image y'all were talking about with the booms. I didn't recognize them as booms because, like you said, they're covered by the blanketing, right? But it actually has the instruments on the boom there. And Dan, what you said is so interesting because you have to think about that. Like, you're out there in space, you don't want to sample the spacecraft, or if you do sample the spacecraft, you almost need to tare, T-A-R-E, the spacecraft. Like, here's what this spacecraft emits, and the different. Yep.
I wish.
But there's some of the instruments that are on the boom, specifically away from the body, so that they can get what's happening around the spacecraft, not the spacecraft itself, right?
Yep.
Right. With the magnetometers, we have one at the end of the boom and one partway down after some very careful modeling. It's called a gradiometer configuration, so that they are in a line away from the spacecraft, you can actually subtract the spacecraft magnetic field by using that configuration. And then one little bit of geekiness that it pleases me so much, I suspect it'll please everybody who's listening. The Gammaray spectrometer, amazing instrument. How does this work? Can I just briefly explain, because I think people would love it so much. We need to get gamma rays that are being released by atoms on the surface of airless Psyche. It only works because there's no atmosphere. And those gamma rays need to come up and hit the crystal scintillator inside that gamma ray spectrometer that we're looking at there. And the crystal scintillator is about the size of a softball, and it's made purely of the element germanium. I've been told that it's the purest material created by humans, and it's green. It looks like kryptonite. And so a question you might ask is, why are the atoms on the surface of Psyche giving off gamma rays that are characteristic of their atomic type that allow us to figure out the composition? Because they are being bombarded by intergalactic cosmic rays. And these come from the edges of the black holes at the center of galaxies and the shock fronts around exploding stars. And they fly through the entire universe all the time, and we're mostly protected by our atmosphere, but poor Psyche is not. And so these hugely energetic events strike those poor little atoms on the surface of Psyche, and when they release their energy, they release a gamma ray that's characteristic of their type of atom. So isn't that just an amazing chain of physics that allow us to figure out the composition from orbit? I think it's amazing.
I was going to try to draw the softball, but I didn't know where to draw it. So Summer, go ahead.
Yeah. Just somewhere in that silver beauty right there.
No, I was just going to say that I love when you are able to do science using the existing universe, just being there.
Amazing.
I had another different wavelength, but equally nerdy question. I saw that instead of transmitting the data back with radio, it's being transmitted with infrared photons.
Okay, Dan, explain. First of all, just to be really clear right at the beginning, we are not using the deep space optical comm laser communications for science. It's totally separable from the science mission. But go, Dan, because this is the geekiest of all the geekiness.
Yeah. And so if we go back to the image before, so the interesting thing about the image of the spacecraft with all the blankets on it is when we get to 16 Psyche, there's the GRNS, there's the imagers, there's the magnetometer, right? Those are our science instruments there. But then the thing that takes up that whole other side of the spacecraft is our deep space optical comm mission, which is its own demo mission. And so when we get to the asteroid, we'll be using our X-band radio telemetry system to get the data back. But what we want to do is we want to say, okay, and this is the other great thing about working with NASA and working with all these engineers, is that there's kind of this parallel path of how do we answer these awesome science questions that will pose the next question of, okay, we thought we knew this, but we didn't. There's the engineering side of, we would like to be better at this. Can we even make this work? And so one of the things we've been trying to do is use an infrared laser to narrow the beam down. So our photons, for radio, the photons will spread out a little bit more, but as we get into the near infrared, we can tailor that beam to make it more not spread out quite as much. And then we can also put more data on it. So we can basically put the same amount of power into something and make it so that we can get better data link out of that. And so that's what the deep space optical comm experiment is. And so it's basically, so this is the instrument, the DSOC, this is the business end of it. So there's that reflector in there. We will send a signal from Table Mountain here in California up to the Psyche spacecraft. We'll point the DSOC aperture at it, and then that laser will get bounced into all those mechanics down there. And then part of the DSOC experiment is to take other data and then send a laser signal back, and we'll pick that up at Palomar Mountain with another telescope that's designed to pull that signal out.
I hope I got kind of close there, Dan. There's a reason NASA doesn't hire me to do their technical drawings, but
I think you're great.
Yeah. And this is a great, I mean, you can see the size, and then if you went back to the other image, you see how big DSOC is. And so
huge.
It's physically large. And then all of this contraption at the end, because we're using this infrared laser at this incredible distance, we need to isolate the DSOC laser system from everything else on the vehicle. So the vehicle itself is pretty stable, it's pretty quiet, but we don't want to corrupt the signal at all. So there's a whole bunch of like cool magnetic actuators and things. So we actually float the DSOC laser assembly separate from the rest of the vehicle. And then even when we're doing that, we ask the rest of the vehicle to be very quiet. And so we do some different things with it. We'll check out in our initial checkout to make sure this all works. And then the DSOC demo mission is awesome. We're going to keep, as we get further away from Earth, we're going to keep testing this link, because when we send, humans out to Mars, or as we continue to send even more amazing science instruments out to acquire more science data, we're just going to want to get more data back. And we're kind of at the limit of what we can do on the RF side. And so this demo here is how will we use a laser to send the data back.
Dan, I have to tell you how I felt the day about 5 years ago when I was told by the DSOC team. It turns out that Psyche's pointing capacity is very good because we can point back and talk right to the Deep Space Network. Not good enough for DSOC, so they're actually going to have to separate from the spacecraft and float in space, stabilized by these magnetic actuators in order to point even better than the spacecraft, and then it'll lock back in again. And I was like, ha ha ha, April Fools, because you do not want a free-floating object like a bowling ball in the trunk of your car. So then you have to have a cage around it. I mean, super complicated.
Yeah.
And just so that is exactly what's happening. It's a technological marvel. And I will just add my final absolute favorite geekiest thing that I learned about DSOC, that Palomar Mountain receiver that's going to receive the laser back from the spacecraft has to be very, very sensitive. And in order to receive the laser, it's an array of, my favorite phrase, superconducting nanowires. And so these little tiny wires are held near absolute zero so that they're superconducting, such that the energy of a single incoming photon from the Psyche laser will pull them out of their superconducting state for just a brief instant, and then we'll know that we detected. And that's not geek at its best. Right. I don't.
Yeah. So, but if they're super cooled, are they completely contained, but yet the photons can get in, or do they have to be exposed to the air?
Dan, I don't know.
I haven't been up to Palomar for a while. I would guess that they have an enclosure with a way that the particular infrared wavelength can pass through, and then it's all enclosed in something that is safe from everything else going on up there.
So
I'm going to go down this rabbit hole after this. That's my third fun.
I have to ask, like, when you said, it has a float free, right? I was like, well, certainly it's not floating free. Like, it's still connected, and you're just saying it sort of needs to be insulated or isolated, or it's on a damper or vibration thing or whatever, right? But it actually floats free, and it's held in place by magnets?
And then there are a couple connections, right? Because
Sure.
we and so it's not actually going to drift completely off in space, but we do, float it with a little magnet there. So it's pretty cool.
Inside its cage, floating free.
No,
isn't that amazing?
That's like not a thing normally. Like you don't normally.
That's
let that
what
happen.
I thought. That was my response, but that's not a thing. And they're like, well, it's about to be a thing.
It's about to be a thing.
It's about
and that's
to.
why it's a demo, right? Because it is so mind blowing. It's like, well, how does this even work? And it's like the team has done all the engineering, and we're like, we think it's going to work. We've proven that it's going to work, but there's all this kind of lingering doubt of like, really? Like, you're really going to do that? And it's like, yeah, we're really going to do it. We're going to go fly it.
I mean,
it's such a thrill to be part of that. And just to say, like, NASA and space in general, very good at unlocking things. We've got the pyro releases and all this stuff. Locking things, not as common. Relocking them.
To like
unlocking
recapture
and
it,
then
right?
relocking. Unlock, relock, unlock, relock.
Yep.
How many times, Dan? A lot.
Yeah.
It's a lot. And being engineers, we put a fair amount of margin on it. The success rate, I forget what the exact numbers for the number of successful opportunities with DSOC to say yes, we pass. And so we basically did, because of the demo, I think we've got almost double the number because all these things need to work, right? The spacecraft needs to be healthy. The DSOC payload needs to be healthy. We need our ground assets, all these other things to go right. And so I don't remember the number off the top of my head. the number I do remember.
Like 60 or something.
Yeah,
yeah.
There's so many interesting places to go just from that. So I want to hit this really quickly. Y'all were talking about locking and unlocking. Remember when James Webb went to space, right? And then it's like all these complicated things have to happen for James Webb to be successful, right? To unfold its arrays in the heat shield and all these things. And it's in the intro. It's like 100 and however many unfolds left to go. It's in our intro video for NSF things. And that was just unfolding. And that's what y'all were sort of talking about, making things unlatch or become disconnected and then go to their state that they're going to stay for the rest of the life of the spacecraft. Do that a lot. That's a normal thing. You fold it up like origami, really small, fits in the fairing, send it to space, then it unfolds and it stays that way, right? But you're talking about something different because it's not just unfolding. It's like you have to recapture it and reconnect it afterwards. And that's, Lindy, what you were saying. You don't do that as much. I mean, I don't want to say NASA doesn't know how to do that. Like clearly a lot of engineering has gone into it, but you don't typically recapture things like that as often as you decapture. That's not a word. I made it up. Whatever.
Yeah. Good.
Gotcha.
Uncaptured. Yeah.
Uncaptured. Whichever. The other interesting thing here. Oh no, we were talking about decapturing it. Oh no, I just talked about that for so long. I can't remember the other interesting thing. Quick, somebody say something else.
We do lock DSOC down for launch, right? So these magnetic lock and unlock. That's once we've launched, we've checked everything else out. We do have the kind of the James Webb style things that we have to release it, and then in operations we do these float and then lock down, float and then lock down. So.
Gotcha. I remember the other thing. It was the bowling ball in the trunk. Which was, you mentioned, imagine you're driving around a car and you have a bowling ball in the trunk and you turn to the right, the bowling ball goes to the left and slams into your trunk, then you turn the other way and the bowling ball rolls around and you stop and the bowling ball hits the seat. And to have an unsecured object that's contained in the spacecraft, imagine what happens when the spacecraft wants to turn itself and it wants to orient itself or whatever. And then you have something flapping around.
That's where my mind was going 5 years ago. But of course, when we say it's floating, and Dan, you can say by how much, it's in a very narrow tolerance. It's not like it's float all around. It's in a cage contained just so that it can be oriented a tiny bit.
Makes sense.
And during those opportunities, we're actually asking the spacecraft to not do anything other than just so the DSOC payload itself will do all of its own pointing. The spacecraft's going to hold position, and we actually ask the solar arrays to not move either, right? Because our solar arrays, you've seen the inertia of those things. So everything's whole, and so during those DSOC opportunities, the spacecraft's not supposed to move. So,
does this a technical difference here, because this is a thing with the International Space Station? Is the spacecraft supposed to hold its orientation, or is the spacecraft supposed to not do any control inputs and just float free?
I'm pretty sure we do have a kind of a special control mode for it, but the analogy for ISS is interesting because we're so far away, which is one of the neat things about it, is that Earth is moving as far as DSOC is concerned. So we actually load the Table Mountain and the Palomar ephemerides for where those are so that DSOC can actually track as they're moving. But in terms of how the spacecraft's concerned, it's like, I'm pointed at Earth, right? And so that's why the spacecraft itself doesn't have to move much, if at all, over the course of the DSOC opportunity, versus for the ISS, for example, right? It's moving in inertial space and the Earth's moving. And so that's a little bit different problem. The steps are still there, but it's different when we're so far away.
Yeah. And specifically, that's from one of the places that the ISS uses that is when they capture a spacecraft, and they have the Canadarm2 trying to capture a spacecraft. They send the ISS into sort of a free float mode because you don't want control inputs moving the thing that your arm is attached to while you're trying to catch another thing. You just want the motion of the arm to be doing it. So the only reason I know that is because I went to Johnson and did the simulator, and they taught me how to capture spacecraft. And like, it goes. So that's what sort of fired that neuron. Hopefully not a neutron in my brain. So anyways, there's another question, a technical thing that a bunch of people were asking questions about. Let's talk about the Hall effect thrusters. We mentioned it briefly when it's like the design of the trajectory is beautiful because of the way that you have to do this. And part of that is because the thrust you get from the electric propulsion, right? That, I think, is a technical detail we should dive into a little bit. Dan?
Okay, so this is an image, not of our particular thruster, but a similar thruster under test. And so that blue glow there, and I'm sorry, the storm's actually starting to come through, so you're hearing the banging of everything around the house.
We're good.
So, but so what we're doing is we're flowing a xenon gas out through, and there's just kind of these little white circles there on the one that's not firing. It's coming out the back of that, in that annulus there. And then what we do is we create that little kind of thing on the upper image there is a cathode, and it's creating an electric field by basically ejecting electrons off. And so those electrons are kind of moving out here. And so now we've got kind of a negative field out here. And what we do is we have a positive plate at the bottom of the thruster there, so at the bottom of the anode. So those electrons want to kind of zoom into that annulus there, and then they want to go to the positive plate, and then they're all happy, right? It's, you know, the negative flowing to the positive. But what we do is that the reason that it's an annulus there is we build a magnetic field across radially out from there. And so as those electrons move through the magnetic field, they get twisted around. And so they actually start doing this kind of circular pattern in that annulus there. And so as these electrons are zipping around in that annulus, as the xenon moves out, the electrons hit the xenon and then they ionize the xenon. And so now the xenon's got a positive charge. It wants to get away from the anode and it wants to run out towards that negative field out there from the free electrons. And so it zips out the back of the Hall thruster. And so that Hall current is the electrons zipping around in that kind of racetrack and the annulus there. So it's super cool. The reason that we love this particular one is that it's very propellant efficient. So there's a reason we do chemical propulsion for launch vehicles. We need to produce a massive amount of power very, very quickly to get out of the gravity and the atmosphere of the Earth. But once we're in space, we don't have to fight the atmosphere. We do have to keep working with gravity, and so that's why our trajectory is the way it is. We're under the sun's gravitational field, and so we're kind of slowly adding kinetic energy to convert that into potential energy and get farther away from the sun. And so we can do this, but the neat thing about the electric thruster is that to produce that power, I don't need a chemical reaction. I'm not reliant on how much energy is in these chemical bonds that I can release that and then let that energy flow into propellant. Instead, I can take the propellant, in our case, xenon, and add energy to it by way of our electric solar propulsion system. So we get the electric power off the arrays. We then we ionize the xenon, and then we build this electric field, and then the ionized xenon flies out the back at about 10 kilometers per second. I'm trying to do the math in my head. It's 10 to 20 kilometers per second. So we get a specific impulse for the space geeks of between 1 and 2,000 seconds, which compares to chemical, which is like 300 to, on a great day, like 350-ish, right? And so we're much more propellant efficient. We just have to be patient, and that's why we're thrusting so much, which is one of the awesome things about these electric propulsion science missions. Is we can be propellant efficient. We just have to be patient. But it makes our vehicle scale down. If we wanted to get the total impulse in a chemical system, it would be a much, much larger system.
Gotcha. Go ahead, Lindy, go ahead.
Oh, just a super brief thing I don't think I ever talked about outside of the team before. So we're flying over a metric ton of xenon. And so because of my background, I've got a bunch of chemistry. I was sort of, well, how many atoms, how many moles are we talking about? And then I started calculating moles per kilometer. And so because it is super, super efficient. So we're doing about 10 to the 18th atoms of xenon per kilometer. And we're going, I forget what the number is, 2.6 million kilometers, something like that, which sounds like a lot of atoms per kilometer, but it's only 3/1 millionths of a mole per kilometer. So that's some gas mileage.
That's some gas mileage. Nice. I may have. Go ahead.
Oh, I just wanted to ask with you said a metric ton of xenon. So what is the design lifetime, and what's the limiting factors for the mission for the spacecraft?
We will run out of propellant at some point in time. It depends on where we are in the mission. That's the other fun thing about the solar electric propulsion. So we're flying 4 of these SPT-140s. They're what our commercial partner Maxar, they fly these on their Earth orbiting spacecraft all the time, right? So that's one of the great things about partnering with Maxar is that they've got this. They know how to do this. So we're flying four. We only fire one at a time because we would eventually be life limited. And I think the life limiting factor is the ceramic on that ring. And so we would eventually run out of being able to use that thruster. Its efficiency would eventually degrade. And so we would swap to a separate thruster. But we're watching our xenon budget very carefully. And then we also have a nitrogen cold gas system for momentum control at the asteroid.
Okay. So what is the design life for the mission or the prime mission?
I don't remember that off the top. So the whole mission, we want to be 99 months long plus some margin. But then the thrusters underneath of that, it's kind of, we would need 3 of them to do, and we're not thrusting all the time. That's the other reason I'm having a hard time doing the math in my head is that we have forced periods of the mission where we aren't doing the thrusting.
That's right.
I mean, I'm an astronomer, order of magnitude works.
Yeah, 10 years, something like that.
Yeah.
It'll be more, 15 years. Yeah, that was one of the things we had to check when we switched from last year to this year, because this year is a longer mission, and we were still well within our design capabilities.
Right. Yeah, Maxar flies these for, they just check that box for us pretty quickly. They're like, yeah, you're fine.
Yeah. So I know we've covered a bunch of really cool, nerdy things, but are there things that we haven't talked about, or also something that you think you're waiting for? Like, what do you anticipate most, or what are you most excited about for this mission to see happen or to see be successful? Or
Dan, do you have an answer for that? I've shared some of my favorite geeky things already. Yeah.
Is like a system engineer, I'm really excited about the team part, and I think Linda, you can probably talk to that too. There are so many moving parts, and there's so many expertise that have they're the geek in this particular thing. We just talked about the Hall effect, and we have of the geekiest geeks with this particular thruster, we have them working on the mission. Of the geekiest geeks about navigation, right? This deep space. How do you get all this to work? We have those people. And it's this awesome, diverse team of all these people who are just so at home, being so excited about this thing that we all get to do together. And it's great to have a home for all of these folks who are excited about spacecraft thermal design, telecommunication, the optics, all of this stuff. That's the cool part in getting ready. To me, being ready to launch, and we were just talking about this in our initial checkout. It's like the first flight image that we get down from the imager, and the first actual mag data, and the first time we start seeing that Doppler when we fire that thruster up, that's awesome. And it's going to be great to just be there with the team seeing all that happen.
I think we have an image of DOS.
I'm sorry, go ahead.
Didn't you send an image of the US at least where all the team members are from, or some of the bigger teams are located? Because it was a good distribution.
I've got that. Just 1 second. How is this?
At peak, our team was about 850 people over dozens of institutions. And right now, I think we're about 350 people. And over the time since selection in 2017, we've had over 2,000 people work on the project. And I'm with Dan. I mean, to me, this is about teams and what humans can do as teams. And to me, there are 2 giant purposes and things that make me excited. One is the fact that systems engineering is a major step in human evolution. I think it goes overlooked, and it's only the last 50 to 70 years that we've been doing this, figuring out how to build things that are so complicated that no person on the team understands how it all works, and yet it works. That is an amazing capacity for humans. And to see this working in space, when we have so many scary, negative, frightening, guilt-filled narratives around us on Earth right now, to see this kind of positive, hopeful space future, what humans can actually achieve, that is a lot of why I'm interested in working in space, because it's inspiring to all of us on Earth to see what's possible. And so one of our goals on this team has been to involve as many people as we possibly could. And we've already had more than 1,500 college students participate with us. We have free online courses that are available to everyone in the world. We have huge amounts of art that are created by student art interns that are really great. And we've already got the pipeline written such that our imager pictures, there's some of our art. Every year we choose 16 student artists, and we fund them to make 4 original works of art. And then we put all the art online in virtual galleries. We've had cooking, we've had jewelry making, we've had concertos, we've had marching band pieces, writing, we've had videos, like you name it. And a lot of it is freely downloadable, the graphical art. So anyway, our images are going to be available to everyone on the internet for free within 30 minutes of our receipt. We are not going to edit them, and we're not going to use the censor. We're just going to let everybody look at what we're looking at. Because that to me is the inspiration. It's for everybody on Earth to look up and say, humans are amazing, look what we can achieve.
That is so well said. Dan, your role as a flight director, is that going to be based out of JPL?
Yes. So there's the team of us flight directors. So David O is our lead flight director, and he's been with the mission since the proposal, right?
That's right.
And so it's great for David to be there to watch, this integrated thing. And so we will, our launch campaign team is out in Florida because they need to take care of the vehicle and the instruments up until launch. And then there's a group of us that'll work at JPL. As soon as the vehicle's in orbit, we'll go ahead and attach that radio signal, check everything out, and make sure it's all doing okay. And then we walk through this initial checkout. And so that's kind of fun. That's the human interaction with all these brilliant engineers as we go, subsystem by subsystem. We check out the thruster, we check out, the flight computer. All of these fun things are brilliant guidance, navigation, control folks, and our mission design folks. We calibrate the thruster using that radio link. And so the team of us, we're really just there to kind of help, right? Because they know they're part of the system backwards and forwards. And as a flight director, we're just, we facilitate. That's really kind of what we do.
For a mission like this, how many people are sort of live monitoring the mission at any given time? Does that make sense? I realize I've never kind of thought about that. Like when you have mission control at Houston, obviously, that's a room full of people. Is it the same for these kind of missions?
It'll vary depending on what we're doing on the day. So on launch day, we've probably got 30-ish people in the room. And then we have another shift of 30 odd people in the other room waiting to come in. And then once we get through this kind of critical activity of getting the vehicle, making sure it's okay, it's healthy, it survived launch, we go through and check each system. And we'll bring the team a little bit smaller, and it might be 20 people per activity. And then what we'll do is overnight, we'll let the vehicle kind of rest while we get all the data down. We have to go process the data and make sure it's okay. And so we have these kind of nice down days for the flight team where it's like, we did this activity yesterday, we have all this data, let's go look at the data, let's make sure that it all works before we go do our next activity. And so the amount of people in the mission support area will vary depending on the day. It'll be 30 plus down to a handful depending on the day.
That makes sense. So strangely enough, we're already running out of time, and I could continue asking questions till the heat death of the universe. But I'm going to throw it to Das to see if there's any more people watching that have good questions.
There are. There's so many great questions that have come in today. I assume y'all can hear me. Yeah, you can hear me. There's so many great questions. Somebody's asking us, we could do an entire live stream explaining what Monte Carlo means. And I'm like, I don't know if we have time for that today.
True. I know, that's really geeky. I endorse that idea.
Is there like a 60-second explanation of what that is or how that works?
Yeah, just running a simulation with slightly different conditions over and over and over again to try to simulate every part of a big parameter space and make sure you understand the edge cases of what can happen. Is that fair, Dan? Would you say it a different way?
Yep. Yeah, and it's super useful all over the place. It's not just for space geeks, and it's not just for us. Like the Mars Intercept landing people do it all the time, but any kind of endeavor where you're trying to understand what your distribution is when you have all these kind of different things that go into it, it's an awesome technique.
I've seen time traveling movies that work that way, where you keep trying the same thing slightly over and over again with slightly different things.
Slightly different results,
yep. Yeah. So there was a big question that was sort of coming through, a lot of different folks asking it, but let's say Psyche goes all the way out there. When it does, it orbits, it does its mission. What happens next? Is it going to stay in orbit around Psyche forever, or 16 Psyche forever? Does it have any other follow-up targets? Is it just going to go until it runs out of xenon? Or like, what happens?
Yeah, so we don't have an approved end of mission plan yet. That won't happen until we are there and kind of get the stamp of success And these things are very tightly prosecuted. We have a document, which is our mission success criteria that we've really thought about them carefully. At what point can we stand up in front of Congress and say, yes, we did it? And then we'll propose an end of mission. And it's probably going to be to circle down, to orbit down closer and closer to the surface and get better and better data about Psyche, because even though there's well over 1 million asteroids in the main asteroid belt, it's a truism to say space is huge and there are not other ones that are close by to Psyche. Hard to go visit another object, but there could be other end of mission plans that come into brilliant people's minds over the next 6 years, and something incredible otherwise happens.
Yeah, because this is an orbital mission. Like, you're not just flying past it, right? And you get your one chance to do your science. You're actually going to go and we always argue about this. Is it inter-orbit?
26 months of orbiting.
26 months of orbiting. So you're going to be orbiting it, and then it's not like, all right, let's fire it up and go to the next place or whatever. That makes sense now that you've said it out loud, to get down closer and closer, especially not knowing how the density is sort of spread around the asteroid and how that's going to perturb your orbit.
Who knows? Yeah, and who knows what we're going to discover when we're there. And people... I think it's weird for a scientist to say everything I say to you now is probably going to be proven wrong, and what my dearest hope is that everything I've said is wrong and it's something even weirder. But that's the situation we're in with this object. We know little about it.
Yeah, I have to say this because what you just said is a thing that a lot of people don't understand about science and exploration. It's not saying that we know all this stuff because we're science, right? It's accepting what you don't know and then figuring out ways to learn it, to get that information to back up what you think might be true or whatever. It's not, here are all these decimal places that prove that we're scientists because we've got 50 significant differences. No, it's more about knowing your error bars and admitting your error bars and saying, here are the things that we know, here are the things that we don't know, here's a plan to shrink those error bars down, learn more things about the universe and everything around us and that sort of stuff. That's science. Right. That whole process.
It's just a technique we figured out to try to get closer to the truth. That's all we're doing.
Yep.
We're edging in.
I think too many people just don't understand that. Like, we don't know, and science is the process of going out there and finding out new things and just expanding our knowledge of the universe.
That's it. That's exactly.
That's
all
what this mission is
out there. Yep. All questions.
Yep. Mm-hmm. God, that is absolutely what this mission
what Dan does. What Dan does is answers.
There you go. Well, no, it's part of the symbiotic relationship with the big team you were talking about, right? The scientist says, hey, here's what we know and what we think we want to know, and then the engineer says, well, here's ways that we can go get more information about that, and you work together to make it happen, right?
100%.
Nice. There's no way I can get through any more questions on this. There was one sort of question that a couple people asked that I'll ask. Have y'all asked the James Webb team to be like, hey, could you take a picture of Psyche for us? Because James Webb takes pictures of everything, and then everybody's like, oh, wow. Is there a reason that it could or couldn't be imaged by a telescope like that?
James Webb totally looked at Psyche in March. We got in on cycle 1. Stephanie Jarmak, this young astronomer, led the proposal, which I was on, but it was not for camera pictures because that was not the most important question. It was actually looking at Psyche in the infrared to see if we could learn more about its surface composition. And so stay tuned for results. We're still marching through the data.
Gotcha. There you go. Excellent. We didn't leak anything, did we? That was published somewhere. Somebody knew that was a thing, right?
Not published yet, but the fact that it's public what was looked at.
Thank you. Public versus published. I'm definitely not a scientist that writes papers. The only other thing I was going to do was wave my methane molecule around on camera when we were talking about the Hall effect thruster, but I don't have a xenon molecule, so we're past that now. I was going to talk about the tyranny of, I got an oxygen and a methane here.
Wrong tirade, sadly.
Wrong propellant.
Wrong propellant. Anyways, we have come here to the end of our show for this month, actually. Lindy, Dan, thank you so much for the time today, taking time out of your Sunday to talk with us.
Oh, thanks for inviting us. This was really fun. Very fun to do with Dan. Yeah.
Excellent. That's one of the things we love to hear, was that it was fun, right? Because we could do all sorts of presentations, and it's important, but to sit here and just nerd out about cool space stuff.
You guys are great. Unapologetic nerddom. It's so great.
Yes.
That is absolutely us. Let me see what our next show is going to be here. I actually probably should have read that before we got into this part, but I'm having so much fun with this show, I didn't actually read up on it. What's happening next? Oh, It's going to be on site. Go ahead.
You're in person next.
Yes, we are. Next virtual Astro Live is actually not going to be completely virtual. We're going to be out there at the Intrepid Museum for their astronomy night on Friday, September 29th. We're still planning on streaming that and sharing that with folks that can't make it to the museum, remote viewers, that sort of stuff. But we will be there. I don't have all the information on what the special event or the presentation will be, but if you're in New York City, you can get there. You can actually go to the museum. They're doing an astronomy night that you can visit in person. If not, you can experience it right here on the same channels you're watching right now. Make sure you like and subscribe or whatever the kids are doing these days. You know where the buttons are on whichever social network you're watching on right now. To learn more and to visit and register, visit intrepidmuseum.org is what it says over there on document. And then also, remember, the streams don't just happen. Virtual Astro Live is supported through a NASA cooperative agreement awarded to the New York Space Grants Consortium. I say that at the beginning, I say that at the end. Hopefully y'all appreciate that, the fact that the shows keep happening. But that's what we're able to do to keep those going. And hey, Jim Cavett, I saw the tip came through as well. Thank you so much for supporting what we do too. For now, that is going to be the end of our show. I didn't brief our guests on this, but this is where we do our very favorite wave as we go away. Make sure you follow the channels if this is the sort of thing y'all like to do. Remember, if you couldn't watch all of this, you came in the middle, you can go back to the beginning. The VOD will be available on demand. Watch it at your own leisure, whichever one that is, so you can get caught up on all the things we talked about here. But again, folks, Psyche launching currently scheduled early in October, going on that Falcon Heavy out of the Cape. Of course, we'll be covering that. Lindy and Dan, y'all will be watching, I imagine.
Oh, yeah. Yeah, I'm going to be in Hangar AE on console, freaking out with everybody else.
Freaking out with everybody else. Excellent. And Summer, thank you so much for joining us here today as well. Y'all know Summer Ash.
I still have so many questions, but I'm okay.
Now we're going to do the after party where we shut down the stream and we talk to them with y'all not watching.
Secret.
Anyways, folks, that is the end of the show here. I am going to try to roll the video because everybody loves the song, but if it's hiccupy, just go watch another NASA Space Live video. Not sure why that was a little stuttery at the beginning there, but thank you so much for watching. Again, Intrepid Museum, Astro Live. We'll see you nerds next time.
And here we go.
Propulsion continues to be normal.
RCPA chamber pressure looks good.
Probably not. Roger, with planet.
Water towers, fly! Yes! Tango down to nominal.
Flight downside SPD off. Say again, SPD off. It's orange! 145! Oh my god! Oh my god! Decollage! What is it? Put that in the big bag, Tingle.
343 unfolds to go.
Indeed.
We rise together back to the moon and beyond.
This methane would be igniting in the flare, correct?